Now, uh, hello everyone. Let me first introduce myself. I'm Jelena. My educational background is in mathematics and computational science, and in the last 10 years, I've been working as a developer using functional programming. It was mostly Scala, but I've had some fine experience with Clojure as well for 2.5 years, and I've been working mostly as a backend developer. But I still have a passion for mathematics, and I find this community as a good group of people who uh, take care of all the good sides of what we do. And in today's talk, I'm going to explore one of the dividing lines in mathematics and modeling, like that is the contrast that we have between linear and nonlinear thinking. Uh, and why do we mathematicians, scientists love linearity so much? Uh, well, because linear systems are the ones we can solve exactly, the ones where superposition holds, the ones where the whole is exactly the sum of the parts. And it sounds a little bit idealized since the real world is rarely perfectly linear. But the linear approach is our go-to approximation. And linear models are attractive because they are simpler and more interpretable. And if a system is linear, we can easily break it apart and understand each piece independently. While nonlinear systems, on the other hand, can exhibit surprises. Two small effects can combine to produce something entirely new, not just the sum of their parts, as we expect in linear case. And uh, our brains like to think linearly, but the universe often behaves non-linearly. So the roadmap of this talk is like, we'll start with the linear foundations, the concept of vector spaces, and example of multiple linear regression, and we'll see how linearity forms the bedrock of so many models. After that, we'll touch on Fourier's analysis, and we will end with some limits of these models and the ways how we found solving them. So yeah, that would be a short introduction on my talk. So let's start from the very beginning, like vector spaces. If you've ever taken linear algebra, you'll recall that a vector space is a collection of objects, vectors, that you can add together and scale by numbers and still stay in the collection. So that's a nice property of vector space. And think of a simplest example, the plane, 2D plane. It's a vector space. You can add two vectors in the plane and get another plane vector, or multiply a vector by some scalar, for example, 3, and stretch it, and you are still in the plane. In the vector space, we have the concept of linear combination, taking some vectors and adding them up, and after scaling by coefficients. And I want you to like visualize this. Imagine three-dimensional space. A basis could be the three perpendicular unit vectors pointing along the x, y, and z axis. Any vector in 3D can be built by adding some amount of x, some of y, and some of z. It's like mixing primary colors. You get all like colors by uh, using some amounts of red, green, and blue. And so there is an analogy with the vector spaces. And it implies that complicated things, vectors, signals, data points, might be expressed in terms of simpler building blocks. And I here put some Clojure snippets that I will do that in most of the slides, just to be aware that Clojure is supporting us in this journey. Okay, so what about linear relationships? In a linear system, outputs respond to inputs in direct proportion. For example, if you have like one input, if you double the input in linear relationship, you will double the output. That's like linearity in the nutshell. And we often restrict ourselves to linear functions because they're easy to handle. And with that small introduction, we can talk about multiple linear regression, which is one of the most widely used linear models. Suppose we have some phenomenon we want to predict. For example, the price of a house based on several features like square footage, number of bedrooms, distance to the city center, etc. And in the multiple linear regression model, we assume the outcome, like house price, is a linear combination of the features. So we can move further. We then model these relations via normal equations. And the power of linear regression comes from its simplicity. So we can easily interpret what is like the input. Those are like features, and the output is those coefficients that we want to find, like in this beta that we have in the slide, in this normal equation, is what we want to find to know what is the weight of the features that we want to add. So let it put less technically. So maybe this previous image is more useful in that case. Imagine plotting data points and trying to draw a plane that fits them best. With linear regression, we are literally projecting the data's outcome vector onto the subspace spanned by the feature vectors. And the result, like the plane we got, is the closest approximation within the linear subspace. And there is a unique best solution. So there is only one solution, assuming our features are linearly independent, and we have more data points than features. So that is, if you recall, like basically solving quite basic equation like this, and I prepared some example in Clojure, and like with the steps, so it's quite obvious what's been done, and in the end we get those coefficients, and we are ready to go if we have some intuition that we have linear dependence between the output and the features that we are relying on. And linear regression is often the first model taught in statistics or machine learning classes. And it's for good reason, because it's interpretable, and we can check the residuals, the differences between actual and predicted values, and often get an insight whether our linear assumption holds. So we sometimes start with that assumption, but like the mathematics tell us if we are right or wrong. Yeah, so to summarize this section, a vector space gives us the language to talk about linear combination, and linear regression is one big practical application of that language. And in regression, we assume that the target outcome lies in the subspace spanned by the features, so plus some noise. And when that assumption is even approximately true, linear regression works like quite good. And when it's false, well, that's like a teaser for things to come when we will discuss nonlinearity. But before that, let's see a bit more of the power of linear methods in action. So this was like the solution of the previous equation. I will now focus on some applied linear methods. I prepared embeddings with large language models, but first maybe it would be nice to start with the principal component analysis method. So our next stop is to see linear algebra at work in some, like, as I said, powerful methods like principal component analysis and large language model embeddings. Both of these are rooted firmly in linear thinking and vector spaces. So when we speak about principal component analysis, let's try to visualize. Suppose you have a data set with a lot of variables. For example, imagine you surveyed people with 100 different questions. That means you can think of each person as a point in a 100-dimensional space, where each coordinate is their answer to one question, suitably numeric. And 100 dimensions is hard to visualize. Our brains like to think in small dimensions, like 3 or 4, maybe geometrically. And enter principal component analysis, which is essentially a technique to reduce the dimensionality of the data while preserving as much variance, like informative content, as possible. So it would be maybe good to understand intuitively how does principal component analysis work. What it does, it finds a new set of axes for your data, new directions in that high dimensional space. So we are in this image having a three-dimensional data set, so we can visualize what's going on. And like in that process, the first axis, which is like the first principal component, is the direction along which the data varies the most. So this is the result, for example. So I want to showcase how it was put into like a lower dimensional space thanks to it, while not losing important information about components that we work with. Yeah, so the second principal component is the direction orthogonal to the first that captures the next most variance. So we can continue like as much as we want, like if we are starting from some high dimensional space and want to go in a smaller dimension. So we are caring about these components. Yeah, if you have a lot of variables, but it turns out many of them are correlated or redundant, you might find that the first few principal components already capture most of the variability in the data. And that means that you could effectively describe the data with just a few dimensions, which are actually the principal components instead, if you recall of that initial example, instead of 100 original variables. So that is a great help in trying to understand some data sets. Mathematically, principal components analysis is accomplished by some eigenvector decomposition, but since today we would like to give some hints of what's going on, maybe not to deep dive, but just to be aware that this is also supported via some algebra. And if you haven't explicitly used principal component analysis, you likely benefited from it. It's used in data compression, noise reduction, and as a pre-processing step in machine learning, if you want to decorrelate features. So it's all linear transformations, rotations and scalings of the coordinate system. So there is nothing nonlinear in principal component analysis, and yet it can reveal the intrinsic dimensionality of data. So if your 100 question survey really had only, say, 3 underlying factors, maybe, I don't know, happiness, income level, and age, like drive most of the answers, principal component analysis might discover that you effectively have 3-dimensional subspace of interesting variation amid the 100-dimensional noise. So that's quite valuable. So I would like to pause, think about what we just said. Principal component analysis is a linear technique. We can often cut with it through high complexity and find an underlying order or simplicity, a lower dimensional structure if it exists. So it is needed that it exists. And then it will be a linear subspace. If your data really is or near a linear subspace, then this is like a great choice, and it will find it for you, and you can work in that simpler space without much loss. So that would be and as an example, I prepared with existing. So some of these libraries are built within the community, and this is like a nice image of what was discovered like in 2D, and we kept all the information from the 3D, but yeah, so that's an example how we can reduce dimension, use some linear methods, and still keep working without any loss. So next, about powerful linear methods, I would like to mention word embeddings. That's quite hot topic nowadays. And if we speak about embeddings, they're, as I said, particularly interested in context of language models, large language models, and that might seem unrelated to principal component analysis at first, but it's all about representing information as vectors in a vector space, which is like the same underlying theme. So if you heard of word embeddings, like there are some projects like word2vec or sentence embeddings from transformers, you know that these methods, so that's quite interesting, represent words as points in a high dimensional vector space. For example, word2vec might represent every word by a 300-dimensional vector. And these vectors are not assigned like manually, they are learned from data such that words used in similar contexts end up with vectors that are close together in that space. So one famous example is this one on the slide. For example, you have that in a well-trained word embedding space, king minus man plus woman is equals queen. In other words, if you take the vector for king, subtract the vector for man, and then add the vector for woman, you get a vector that is astonishingly close to the vector for queen. And this suggests that the concept of queen is in some sense king plus femininity minus masculinity encoded linearly. Like the embedding has captured, like we got that the embedding has captured the gender relationship as a direction in vector space. So that's a linear analogy. Similarly, there's like also Paris minus France plus Japan equals Tokyo. So it can also capture the capital city relationship in another vector offset. So it feels like magic, but not exactly. It's picking up statistical patterns, and those manifest as linear directions. What is the key point? The key point is that high dimensional vectors can encode complex relationships, and linear operations on them, adding and subtracting, can result in meaningful transformations. And modern large language models like GPT also operate in a very high dimensional space of embeddings. Each word or subword token is embedded in a vector, and the model processes sequences of these vectors. So as I heard, like Paula will give a great discussion about LLMs in like the next talk. So here I will be short. This slide is maybe showing too much, but I would like just to give like a brief explanation of what is it about. Like it shows how LLM embeddings happen. Like we have a journey from tokens to vectors, from discrete tokens to continuous vector representation. So first we have token embedding, where inputs are tokens, words or subwords, and they start as one hot vector. And then we have transformation multiplied by a learned weight matrix to map them into a dense vector space. And as an example, we can have a vocabulary of 50,000 tokens, and project them into in this like the examples like 768 dimensional space. Like that's the first phase, like token embedding, and then we have some neural network work like self-attention and feed forward. Each transformer, we have transformer blocks where each transformer applies linear projections with queries, values, and feed forward weights. And we have nonlinear, that's like when nonlinear happens, nonlinear activations such as softmax for attention weights or GLU or ReLU. And this is alternating pattern, linear, nonlinear, linear, nonlinear, and we have this composition of repeated layers, like a stack of like up to, I don't know, 100 transformer blocks, and with the idea to capture increasingly complex patterns. So early layers do basic syntax and local features, while deeper layers do semantics and long-range dependencies. And as final output, the model outputs a high-dimensional vector. For example, with BERT base, like in this are with the 768 dimension, and can like final output can represent a word like from one token or a sentence. So key takeaways are that embeddings are built via hierarchical transformations, so simple towards complex, and with linear operations such as multiplications and nonlinearities, GLU, softmax, and all which work together. So that would be like a short explanation of this slide. As I said, Paula will give you much more in terms of this subject. We went through principal component analysis. And yeah, so next example, which I would like to speak about, and it is related with linearity as well, is famous Fourier's analysis. And in the early, so this is quite old from, if you take a look, like in the early 19th century, the French mathematician Joseph Fourier, he made the claim that any periodic function, like any repeating signal, can be expressed as a sum of simple sine and cosine waves. And that was, as every novelty, met with skepticism by the mathematical establishment of that time. But it turns out it was a revolutionary idea. He was correct, and his insight gave birth to Fourier analysis, which is like a cornerstone of modern applied mathematics and signal processing. So what does it mean in our context? It means that the set of sine and cosine functions of various frequencies, so you can see I put bases here, like you have this k, which is in control of frequency, that forms an alternative basis for the space of periodic functions. Yeah, so think about that for a second. This is like a Fourier's trick was essentially to change a basis in function space. So we first, you learn to express points in 3D with coordinates. Then you learn you can change bases for convenience. And finally, we have like the vector space as space of functions. So a different basis, sines and cosines, would be better suited for like some of the problems. And such problems are like heat flows, sound waves, or electrical signals. The sine and cosine basis is tremendously better suited than like a standard basis like pointwise samples or monomials. So Fourier transform is essentially rotating to the basis in an infinite dimensional space. So because this k is a natural number, like as you know, we have infinite number of natural numbers. So here on the right side of the slide, we have a square wave approximation with Fourier series. So like Fourier series is linear in terms that you have a summation of these sines and cosines with different frequencies. And let me explain this image on the right on the slide. So on the top left, you see that using only the first sine term gives a very rough approximation. As we add like the third and fifth harmonics, that's like on top right and bottom left, the approximation improves. Like by 11 terms, which is on like bottom right, the Fourier series closely, you can see like that it really closely matches the square wave, except for tiny ripples. So this illustrates how any function, like in this example is a square wave, can be approximated by linear combination of basis sine waves. Yeah, so this was like just a short example to have an intuition of what's going on, but the impact of Fourier analysis in real world data science and engineering like cannot be overstated. Whenever you use an equalizer on music or some image compression, then MRI, medical imaging, or any kind of spectral analysis, you are using Fourier's linear space idea. For example, noise filtering. The Fourier perspective reinforces the core theme. Linear bases matter. Like by choosing the right basis for the right problem, complex phenomena become simpler. A periodic signal that looked complicated in time domain becomes a neat set of spikes in frequency domain. So there is a lot of mathematics that we use there, such as integrals, orthogonality, coefficients. But here we use them in like an infinite dimensional setting, because as I explained, this basis is infinite. So before we move on, like the analysis formula for Fourier series affects a change of basis. It is a rotation in the space of 2p periodic functions. The synthesis formula like undoes the change of basis. In other words, when we go to the frequency domain, we've simply rotated our viewpoint in functional space. And when we come back to time domain, we rotate back. It's like linear algebra through and through. I also prepared some, as I said, code snippets. We have support for Fourier analysis in Clojure via Neanderthal, so you are free to try. Yeah, and we have now seen 3 chapters of our story, like fitting data in subspaces via regression, finding structure like via projection. So we were able to find real structure with principal component analysis. And now with the Fourier analysis, we are changing bases in function spaces. Yeah, so it's time for the final chapter. So let me move further. So we come to limits of linearity. This is like a Swiss roll example, which was like a famous example, which was showcasing why linearity is not solving all our problems. So maybe it would be better to present this second image, like how, where it is shown how principal component analysis cannot unroll Swiss roll. So look at the image on the left. What are we seeing? We have points in 3-dimensional space forming a shape that looks like a rolled up ribbon or sheet of paper. So that is why it's called the Swiss roll. What is interesting here, that this data set is actually intrinsically 2-dimensional, despite living in like 3D ambient space. You can imagine unrolling that ribbon into a flat sheet. The data would then lie on a nice flat 2D rectangle. But in its roll state, it's a 2D surface non-linearly embedded in 3D. So why do we care about this? Because this is a great illustration of where linear thinking can fail. Suppose like if we applied principal component analysis, like with this linear dimensionality reduction to this Swiss roll data. You can see the image on right, what happened. So what does happen? Like PCA would look for like the directions of greatest variance, as we explained before, in the 3D space. The Swiss roll, being a bent sheet, has variance in all three original dimensions to some extent. And PCA might find one principal component across the spiral, maybe roughly pointing diagonally through the roll, and the second one perhaps orthogonal to that. But PCA cannot unroll the Swiss roll. Any straight line projection of this data will inevitably mix together points from different parts of the roll that happen to be above each other. So you can see that we don't have right feeling of what's Swiss roll after we projected it via principal component analysis. So think about 2 points that are far apart on the rolled sheet. Along the sheet, they are far apart, maybe different colors in our figure, but in the 3D space, those 2 points might actually be adjacent, one almost directly above the other in the vertical direction. And a linear method that uses straight line distance might consider them close, even though on the manifold of the sheet they are far apart. So in other words, linear methods operating in the ambient space can mix up the structure. And that is like, since we are now speaking about limitation, that is a fundamental limitation. Linear models can see the world as flat. And if your data actually lies on a curvy manifold, like this Swiss roll, linear models will struggle to capture that shape. And what they will try to flatten it with a hyperplane or a low dimensional linear subspace. But some relationships will be lost or distorted. And for the Swiss roll, principal components analysis best to this subspace can at most capture a shadow of the structure. So it looks like a blotch of points without the nice unrolled order. So this Swiss roll example became classic in the early 2000s when researchers in machine learning were developing some manifold learning algorithms. So the Swiss roll reminds us that not all structure is linear, so we should have that in mind. And there are relationships in data that are not straight line or flat plane, or can be captured by a flat plane. So the limitation of linearity is basically assume linear at your own peril when the true underlying shape is nonlinear. Fortunately, there are ways to handle this. So in this part, we will speak about some nonlinear methods that help us in respect the curve structure of data. And in the case of the Swiss roll, we want a method that can learn the manifold structure and effectively unroll it. And that is where algorithms such as TSNE, UMAP, and autoencoders come into play. So let's step into the realm of non-linear methods just to see how we can go beyond linearity and tackle cases like the Swiss roll and many others. So we will discuss few popular techniques and ideas. Once we acknowledge that not all relationships are linear, that opens like a whole new toolbox. So nonlinear methods come in many flavors. There are nonlinear regression models like polynomial regression, neural networks, etc., nonlinear classifiers. And here I will focus on dimensionality reduction. So we had dimensionality reduction before with principal component analysis, but it was like in a completely linear setup. And here we are like in a non-linear realm. And we will see how some feature learning tools that are explicitly designed to handle cases like our Swiss roll on more complex high dimensional analogies. Okay, so let's speak about a few of them, like T-distributed stochastic neighbor embedding is a method particularly well known for visualizing high dimensional data in 2D or 3D plots. And its goal is to take a set of points from a high dimensional space and produce a lower dimensional embedding, say 2D for plotting. And the idea is to preserve local neighbor like relationships. So in plain language, what does it mean? Like if 2 points were very close in the original space, meaning they were similar, this method will try hard to place them close in the plot. It doesn't worry too much about preserving large distances or global structure. Like it focuses on getting the small distances right. And this often leads to beautiful visuals where clusters in high dimensions turn into obvious clusters in 2D. So one great example where this worked is a data set of handwritten digit images where each image was like a point in like, I don't know, it doesn't matter, but it was like more than 700 dimensional space of pixels. And after running TSNE, you get like the points which were forming clusters corresponding to the digits from like 0, 1, 2 towards 9 in the 2D plot. So it was able to discover digits from like the data set. So even though the algorithm itself doesn't know what the labels are, like it was like unsupervised, but it was able to cluster and to find like 10 exact clusters. Yeah, so that was, I guess, enough about this one. Next is a new arrival, like quite new arrival, uniform manifold approximation and projection is the full name, like UMAP in this slide. It's a newer arrival, like it's maybe from 7 years old, and it became quickly popular for the same tasks as TSNE. At a high level, UMAP is also a nonlinear dimensionality reduction technique, and it emphasizes both local and some global structure, and it's built on some theoretical ideas from topology, assuming the data is roughly distributed on some manifold. So it tries to learn an embedding that preserves, like the idea is to preserve the manifold structure. And in practice, what happens is that many people find that UMAP tends to preserve more of the global relationship. So with TSNE, it was more about preserving local distances, while with this one we preserve global relationships. For example, clusters might be positioned in UMAP such that their relative distances have some meaning, whereas TSNE sometimes just splatters clusters wherever as long they're separated. So also there's some great mathematics behind, but it's constructing like fuzzy topological representation of the high dimensional data, like a weighted graph of nearest neighbors, but maybe that's too abstract at this point to speak about. And what would happen if we apply UMAP to that Swiss roll? It would likely manage to produce a nice unrolled ribbon in 2D. In fact, many such algorithms were explicitly tested, as I said, on Swiss roll to see if they could recover the right 2D manifold. And these methods are good because they compute distances along the manifold rather than straight Euclidean distances. So by preserving those geodesic distances, they succeed in unrolling. So, and what one more is left is autoencoders, which is also dealing with some dimension reduction and embedics. Let us first define what are autoencoders. They are type of artificial neural networks designed to learn efficient encoding of a data. So every autoencoder has two parts: an encoder, and what does encoder do? It maps the input data to a lower dimensional code, and a decoder that maps that code back to an output, reconstructing the original input. And we need to train the network so that the output matches the input as closely as possible. So it's quite maybe complex to deep dive, but what's interesting to say, autoencoders, they gain popularity for tasks like image denoising. You can train the autoencoder to reconstruct a clean image from a noisy input because it's learning a robust feature representation, and it does this dimensionality reduction that we spoke about. Similar goal as principal component analysis, but more powerful. So they were also a stepping stone in deep learning history. Before we had very effective training for deep networks, people used stack of autoencoders to pre-train systems. So maybe it would be nice to have a summary here. So these methods are non-linear projectors used for visualization, and that's for TSNE and UMAP. And autoencoders are like trainable but non-linear principal component analysis that can compress and reconstruct data. And all of these methods, they like what we started with, they confront the limitations of linear methods, because what they do, they allow nonlinear transformations, which is like twisting, turning, or to better capture the true relationships in the data. So the insight here is that many real world data sets lie on a low dimensional but nonlinear manifold within a high dimensional space. So that is the moment where we can think about using these methods. So let's take a brief breath here. We've covered a lot. from basic vector spaces to some nonlinear embeddings. And what can be a key takeaway here is that linear methods are powerful and often our first resort, but we also have a lot of nonlinear techniques to use when linearity fails shortly. And next, to really drive somehow how widely nonlinear behavior can differ from linear, we'll, for like the ending of this talk, we'll discuss chaos theory and the famous like Lorentz attractor. So if linear systems are predictable, chaotic nonlinear systems are the opposite. They are sensitive and seemingly unpredictable, even though they are deterministic. So this is like this image here shows that Lorentz attractor. That's a famous chaotic trajectory in a three-dimensional phase space. And the system traces out a pattern which is resembling a butterfly. So let us go in history to see when this happened. In 1963, like Edward Lorenz, he studied like a simplified mathematical model of some atmospheric convection. Like that was a toy weather example. And he used some complex Navier-Stokes fluid equations, like those are differential equations, and pare them down to just three coupled. So he simplified that initial model to just three coupled non-linear differential equations. So forgive me if like we are speaking about some higher mathematics, but that is just to have a picture of what was going on, that there was, although there was a simplification, when he simulated these equations on a computer, he noticed something like astonishing. When he made like tiny differences in the starting conditions, that led to huge differences in the outcomes down the line. And this is famously called butterfly effect. So it's like often stated as the flat of a butterfly's wings in Brazil could set off a tornado somewhere in like Texas. So what this work showed, and it's important, is what we now call sensitive dependence on initial conditions. In certain nonlinear systems, any small uncertainty in like where you start will explode into a massive uncertainty in where you end. So so the Lorentz system equations are three interlinked. I didn't put them like in the slides, but there are just three, and the trajectory loops around in a sort of figure-8 pattern, never exactly repeating, but also never flying off to infinity or setting down to a fixed cycle. It's attracted to this butterfly shape set. Hence, like we use that term as attractor, meaning that many different starting points will spiral into the same overall shape of motion. So yeah, so the Lorentz system, by contrast, is nonlinear. That non-linearity allows for feedback loops and energy transfer between scales. This is a deterministic chaos. There's no random coin flip involved. The equations are purely deterministic, yet to any practical observer, the outcome seems random because it's impossible to measure the initial state perfectly. Any uncertainty grows exponentially fast. So maybe I'm speaking too many details about this Lorentz attractor. But the idea was that some small changes in some nonlinear systems can lead to quite big changes in the outcomes. And I would like to make some conclusion at this point. So what I spoke in this lecture, we discussed linear versus nonlinear, and I would like to give some final reflections. So we saw that linearity is a powerful simplification. We had linear models, vector spaces, linear regression, principal component analysis, Fourier, etc. Those are the backbone of so much in mathematics, science, and engineering, because they make problems tractable, and they assume some proportionality and superposition, which often gives us reasonable first approximations. And the success of linear methods where they apply is a proof that the idea make everything as simple as possible, but not simpler. Linear models are about as simple as mathematically as it gets, but they are not too simple if the situation is roughly linear. So then they are perfectly fine. But we saw the other side of the story, because the world is not fully linear. And eventually every model in this world has its limits. And there are twists and turns in real phenomena, like we saw with this Swiss roll, and with the complex interactions in climate system. When a linear assumption fails, it fails in telling ways. We saw that with that Swiss roll example, no linear flattening could unravel the spiral. We also know many relationships, like population growth or stock market dynamics, are inherently nonlinear. They might accelerate, oscillate with growing amplitude. So while linear models are often our starting point, we have to be prepared to go nonlinear. And yeah, so nonlinear methods can capture complexity, but yeah, often with a cost. The nonlinear techniques we discussed are powerful, yet they have complexity of their own. They are harder to interpret. It's not straightforward, as we see, to explain why TSNE placed points the way it did. So there is not simple equation. It's not easy to visualize why those methods work the way they do. So we saw autoencoders features aren't as directly interpretable as principal components sometimes. So nonlinear models often require more data to fit as well, because they can twist and turn in so many ways. So we need to cover all those ways. And there are much more degrees of freedom to learn. And also what we saw with chaos, nonlinear models can be sensitive. So we need to be extra careful in validating them and understanding their behavior. So I think that was enough of me talking. I didn't hear any questions during this talk, but the idea of this talk was to see how we start with something simple, how we build along the way, and how we can fight with some more complex phenomena to explore some new world and to adjust to certain problems. So yeah, that would be my presentation. So feel free to ask or whatever. Thank you.
Thank you, Jelena. That was a comprehensive dive into,
I hope you didn't fall asleep.
No, a
Nice.
lot of things covered. So uh, let's see.
Well, yeah, it
Yeah.
was maybe too it's not like these are all of these are interesting topics and happened in like different times in history, and I believe each of these would be much more comprehensive if it was done separately. So this was more like planned to combine some different things, and I believe that talk that is coming after me about large language models will give much more overview on certain topics. But this was more like brief overview of some historical development of finding different models, solving different kinds of problems. So yeah.
So I had a question and I posted in Zulip as well. So you mentioned that PCA is often used in compression. So can you tell us a little bit more about it? Like what, uh, where, what technique uses PCA, and is it mainly for textual data or audio video data?
For textual data, um, well, I can speak like from the mathematical perspective, where like I was using like uh, having to uh, find eigenvectors, eigenspaces. So when we speak about text, like the idea is, as I said, to convert that text to vectors. So I remember there's some bag of words, and then you can like count word frequencies without normalization. But you can also prepare like the matrix where rows will be documents or sentences and columns like features. So the idea is to reduce like the dimensionality of these initial vectors, and then to, I don't know, that's like I can give you some what during some maybe studies or what I met, but I don't find myself as an expert in application of principal component analysis. But yeah, I remember that there are some like the idea was to build those vectors and then to build projections by finding eigenvectors of your initial space and then working in smaller dimension. And like it's good for probably for pre-processing, like to reduce feature size before you want to do some clustering or classification. So
Yeah, yeah. Just want to say that I'm so glad you took the time to explain PCA as like the center of this talk. For me, that is something that when I learned linear algebra, I thought I would understand, and then people tried to explain to me PCA, and it took a lot of time to get a sense of how it behaves. And the way you explained it today, it was so helpful for me to gain intuition about it, about when it fails and so on.
okay, thank you. Well, yeah, this talk is more about intuition, as you say. It was not a deep dive in any of these particular subjects, and as I said, all of those deserve some special talks, so people would really have an awareness of what's going on. But this is more of like an introductory and talk where you just speak about the intuition and motivation to work on some models.
Yeah, and maybe just for the context, we could mention that a few of the topics will be mentioned in other talks, and that is why it is so amazing that you could collect these things as the core of background for this conference. The Lorentz system will probably be mentioned tomorrow in the weather forecasting talk of Ram and Naimish. And Navier's talks will be mentioned briefly, at least in Xiang's talk about fluid dynamics. And of course, all the linear and LLM parts will be now in Paula's talk. And the Fourier analysis will probably be in Lorelai's talk about EEG and brain data today. So it was such a nice collection of background for these whole couple of days.
Oh, that's like, then it's great that people will also have a chance to deep dive into each of these methods specifically. And I'm happy that this conference will allow that spread of knowledge. And yeah, happy to participate here and be with all of you. Okay, is there any more you would like to discuss? So is there like, I would like to ask, because we spoke about my interest was that UMAP algorithm and applications in data science. So you mentioned that there might be an initiative to do that work in SciNoj or in some later stages. Do you know how it goes, if there are people interested in building such library?
I think these are exactly the questions we should be asking now. And tomorrow there will be a session, the macro expand session tomorrow, where we will be asking ourselves about our hopes for the coming period, what projects we should take on. And I know, Jelena, you had a few proposals from your research about certain mathematical methods, and maybe you wish to say more about that if you wish, about the things you do and things you have been doing. And yeah, so I think it is a good time to ask. And yeah, we should be careful with picking projects, but probably we should.
Yeah, I'm just curious to see, because there's like quite good work done already, and this is like a data science community in a way. And for example, topological data analysis is something I'm interested in, and I believe it would be good if we could form a group of people that will maybe develop some algorithms. There is already great support in Python libraries, so maybe we can use some knowledge from there and just integrate in this community. So just to spread, like, as I said, it's nice when people can change paradigms and can work on. So someone raised the hand. Sorry. So I see Sam and Paula raise their hands. So feel free to ask.
I'll jump in first. The I know the NVIDIA group. There's an NVIDIA group specifically working on algorithms in the Python space, but it's all being written in CUDA, and which means it runs on the card and just has wrappers around it, and then those wrappers get wrapped in Python to access. And there's no reason we can't get to that through the JVM. And I've been very interested in trying to implement some of these algorithms because I've been learning many of them lately, and learning how to use them is very different to implementing. When you implement, you learn a lot more. And I'd like to go through that process just so that I understand it better.
Well, I'm happy to hear that. So, yeah, Daniel, you hear this, and please make this group of people to work on those algorithms. So there are people interested. Thank you, Paula. This was really nice comment, and in the right time, I would say.
Cool. Yeah. So, I just wanted to say that I've had like particularly good experiences using some of these algorithms through libpython CLJ. Every once in a while, I'll get something like tricky with like memory management that'll pop up through the Java Python interface that I can't quite figure out. But yeah, for a lot of these things that are available in Python, I've had I've had really good experiences just calling them through libpython CLJ.
Yeah, well, Python is a winner in these things, but I think that we can learn, as Paula explained, like we can learn and we can enrich the community, like by building the support for, as I said, topological data analysis, which is quite important nowadays. But yeah, thanks, Sam. That's quite true. Siavash, please. You raised your hand as well.
Yep, thank you, Jelena. My question is, did you build any LLM like Llama 2 or 3, anything with Neanderthal? Did you implement it yourself?
No, because as I said, my interest is somewhere else. This was more like a proposition from Daniel to explain it as one of as part of the journey, where like linearity also is something important. And it's because the idea of this whole conference was to speak about something that is up to date. But I think that also with large language models, we can try to experiment within this community. And you seem like a person who has great knowledge about it. So I would like to participate in that kind of project as well. So, but I need to say in my own name that I didn't build anything like that. But feel free to propose, like it's a great moment to do so. Okay, Daniel, I think that we are done with question section. Maybe it's a time.
Okay to ask. Yeah, oh, sorry.
So go on, go.
Is it okay to ask a little bit about the thing you've been doing in your math work? And you mentioned topological data analysis. Could you try to make sense of it in a few words for us, if that's convenient?
Okay, well, I was like mostly interested in distinguishing like communities in complex networks, which are dealing with networks with so many nodes, and that's quite young research field because before we were quite restricted by computational power. We were not able to distinguish communities in such a big network. So I was working like on some numerical optimization problems where I had to find hubs, and previously they used some exact solvers which were like limited to 200 variables, and even with that was like a huge limit because it took like 2 days for that system to find the right solutions. While with the techniques in complex networks, you can quite easily approximate those like hub nodes, for example. That is what I started with, and then I transitioned towards topological data analysis, which is also good for big data sets. It's good for denoising, and in my specific research right now, I was focused on building like projections. So it has some connection with this dimension reduction at first, and then using some topological, because topological community detection algorithms, they're focused on 2D manifolds or some Riemannian manifolds. But you have like a good tools in Python to do the embeddings, and then with these topological algorithms, and they're quite so I was surprised when they were giving like state of the art like results for some famous data sets. So it gives like a direction. That's a good direction to go, but it takes, as everything, like people who are interested enough to spend their time on it and to develop some new algorithms. So what Paula proposed today, I think it's a good way to like start and give your energy to some ideas and understand it on your own. But yeah, the idea, like nowadays we are dealing with a lot of data. and it's all about finding ways to effectively solve those. So we are not able to be exact in these days. That's what's important. But mathematics gives us still quite good tools to fight with that dimensionality, and so it's all about making things simple. How we can build something simple that still gives us enough of information about the point from where we started. And so that was the idea of this talk. Okay.
Saivash, you have a question, please. Okay.
Yes, yes. I want to know how much computation is required for researching in topological data analysis. For example, what is minimum required GPU, as I think it is required more computation power in comparison with traditional analysis.
Well, it's not comparable to large language models where you are using tremendous amounts of computational power. So it's not like that. But still, when you are like trying to, I'm speaking about the position of a student who wants to do some research on their own on their laptop. So they are not. There are a lot of limitations there. So it would, for that kind of research, that it would also require some additional resources, but if we have like that computational power that's being used for large language models, I believe we will not have that obstacles. But I think that for LLMs, like there is a lot of computational power used, and it's not comparable to anything else, because there you are dealing with like billions of parameters. So it's really crazy what's going on. So it's not the focus is not there, but the idea is how to visualize, because if you're speaking about clusters, I don't care to have like too many dimensions, because I cannot see it. Like if I want to see communities, I want to like be able to perceive it with my own mind. So we need some simplification to have that understanding. It's not like the same approach as in case of large language models, where we are relying on some big computational power that will give us all the answers. So here it's a little bit, I think, different direction of researching. But yeah, it's not the same problem as in large language models. So to answer.
Maybe I'll just say that yesterday or the other day, Jelena actually hoped to tell so much more on this talk. And we had a call with Kiran and myself, and we were asking Jelena, please slow down so we can follow. And I think I'm glad you slow down for this talk. And yeah, there is a hope to talk about so much more on other times.
Okay, but let's build something. Like I'm good at talking, but I should be better at building. So I think that's the. Okay, thank you, thanks everyone
Thank
for
you.
joining this talk, and it was a pleasure speaking with you, and yeah, and great to be here. Thank you.
Thank you, Jelena. Great talk to you. We can take a small break now.